All right, so we are in Chapter 10. Chapter 10 is our final chapter of this term. You guys have done a great job so far. You'll be happy to know that Section 10.1 has zero math involved. You can put your calculator away. You can just sit back with your notebook and take your notes, or even better, print off the PowerPoint and take your notes directly on this. And just be thankful 10.1 has no math. Of course, 10.2 and 10.3 will come back with the math, but 10.1 is all about learning about hypothesis testing. So the first thing we're going to do is we're going to determine the null and alternative hypotheses. We're going to explain type 1 and type 2 errors and then state conclusions to hypothesis tests. Now, there's always questions in the homework and on the test about type 1 and type 2 errors, but in real life, this is more something we use to accuse people of doing something wrong rather than using it in our own work. So let's take a look at chapter 10.1. So a hypothesis is a statement regarding a characteristic of one or more populations. We're going to look at hypotheses regarding a single population parameter. So we're going to be just taking one variable and we're going to be using hypotheses regarding that variable. And hypothesis testing is something that several people in the past have used in their final projects. And I'll kind of tell you a little bit about what that could look like in a project after we go through what it is. Okay, so here's some examples of claims regarding a characteristic of a single population. In 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So this would be your claim. So based on data that they've found about past, about something, a study that is done in the past, and then they're going to make a statement about what they think it is now. Here's another one. According to a study published in March 2006, the mean length of a phone call on a cell phone was 3.25 minutes. A researcher believes that the mean length of a call has increased since then. Now, they're not doing any math about it. They're just saying their beliefs. And this belief could be based on nothing other than just an idea you have. They may believe that it's longer than that because anything short somebody has to say might be sent through a text message. So if they make a phone call, it's automatically going to be longer. It can be whatever reason. This is just them making a claim saying, I think it's going to be this way, and then they will do all of the work to prove it or disprove it. Here's another one. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. So there you go. They got some new equipment, and they think because of this new equipment that their standard deviation has decreased. So this means that they believe now that all of the values are going to be closer to the mean. They're going to be closer to the average amount of wine in a bottle because now their equipment is better. So just for whatever reason, you're making a claim that you think something is different now, and then you go about to prove it later, and I'll show you how to do that in 10.2 and 10.3. Okay, so with these types of statements, using simple data, because we can't usually access the entire population. You're not going to be able to look at every single bottle of wine or every single cell phone user, or I don't even remember what the third one was, but you can't look at every single person in the population. So it is using sample data. And if we could use the population data, we wouldn't need to have margins of errors, and we wouldn't need to have confidence intervals and all of that stuff because we'd be looking at the entire population. So it's based on sample data. So hypothesis testing, we use sample evidence and probability. We use it to test statements regarding a characteristic of one or more populations. So we're going to use it to test the hypothesis to see test our data against the null hypothesis to determine whether the null hypothesis is true. So that's what we're going to be doing. Okay, so here's our steps on hypothesis testing. First, make a statement. We read 3 statements. So you're going to make a statement saying, I don't know, 80% of all people, will drive through the yellow light rather than trying to stop. Say that that's what a study has shown, and I think that number is smaller. There's my statement. So then you collect evidence. So you guys are in the process of doing that. Actually, most of you have it done because I've received your data. You collect evidence, you collect your data in order to test the statement. Here we're not testing it yet. That's coming next. You're going to analyze the data. So we're using the what we're going to show you, what I'm going to show you in 10.2 and 10.3. You're going to use that data to assess the plausibility of the statement. So you're going to test that data against the statement that you made. And then, of course, you'll state your conclusion. And I'll tell you how to state a conclusion in a moment. So a null hypothesis is denoted with H. This is called H naught. That's how we read this. H naught. H naught is a statement to be tested. The null hypothesis is a statement of no change, no effect, or no difference. We assume that is true until the evidence indicates otherwise. So we would, like the statement I made about going through a yellow light, we're assuming until I prove different, we assume that study was correct. We assume that 80% of people will go through the yellow light rather than attempting to stop. So that is our null hypothesis. We assume that is true until we show otherwise with our own data. So that is our assumed true. So what is given to us is our null hypothesis. Alternative hypothesis, we denote that with H sub 1 or just H1. It is the statement that we're trying to find evidence to support. So when I said that I thought that number was less than that, that would be my alternative hypothesis. So we're saying that that's what we're trying to prove or trying to find evidence to support. So when we take our sample, we are trying to support our alternative hypothesis. We'll do some examples so you can get an idea of what is what. Okay, so there are 3 ways that you set up the null and alternative hypothesis. Equal versus not equal. So if I say that my null hypothesis is some value, and then I say my alternative hypothesis is different. I say it's different today. I didn't say if it's less than or greater than. I just said it was different. That is a two-tailed test. So I think our very first one was that 62% of American adults regularly volunteer their time for charity work. And the researcher believed that percent is different today. So he's not saying whether it's greater than or less than. He's just saying it's different. So this would be a two-tailed test. We have our left-tailed test. So my null hypothesis would be equal to some value. So my null hypothesis would be equal to some value. So for example, with the old manufacturing process, the standard deviation of the amount of wine put in the bottle was 0.23 ounces. It's equal to some value. And then our null hypothesis uses less than. So we're saying that we believe the standard deviation is less than that value now. We believe it's less than 0.23 now. It's a left-tailed test because because we're looking at the stuff in the left tail. Next, greater than. So according to a study published in March 2006, the mean length of a phone call on a cellular telephone, 3.25 minutes. That would be our null hypothesis because we were saying it's equal to something. And then when we say greater than, so a researcher believes that the mean length of a call has increased. So he believes that it is now greater than that. So that is a right-tailed test. So depending on what we're looking at and what we're trying to prove, we have the left tail and the right tail or the two-tailed test. In other words, the null hypothesis is a statement of the status quo or no difference. It always contains a statement of equality. Always contains a statement of equality. The null hypothesis is assumed to be true until we have evidence to the contrary. We're seeking evidence that supports our new statement, the alternative hypothesis. We are looking for evidence to support our alternative hypothesis. Okay. So for each of these, and I kind of gave you all the answers. I forgot this was on there. So I gave you all the answers, but let's talk about left-tailed, right-tailed, and let's set these up. So for each of the following claims, determine the null hypothesis, alternative hypothesis, and whether the test is two-tailed, left-tailed, or right-tailed. This is also going to show you how we set this up or what this is going to look like, because you're going to be seeing this in your homework. So in 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So let's take a look at this. So we're dealing with a population proportion. If the percentage participating is no different than in 2008, it will be 0.62. So null hypothesis, this is how we would write it. Just like this. H naught, not this ugly. H naught, and then our colon, P equals 0.62. Because we were using a population proportion, we use P. Since the researcher believes that the percentage is different today, so our alternative hypothesis is a two-tailed hypothesis. So take a look at this. So it's H1 colon, and its P is not equal to 0.2 or 0.62. The reason that we know that this is a population proportion and not a mean is because it says the 62% of American adults. And the researcher believes the percentage is different today. So we're going to be dealing with the population proportions and means. So look for those words, look for those keywords. If you don't see the word average or the word mean, then it is a population proportion. Let's look at the next one. According to a study published in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes that the mean length of a call since then has increased. Okay, so let's take a look. So we're dealing with a population mean, mu, because it says that the mean length of a telephone call, and we believe that the mean length has increased. So our null hypothesis would be H naught colon mu equals 3.25. Because we're dealing with a mean, we use mu. The researcher believes that the mean length of the call is increased. So we do H naught, is mu is greater than 3.25. So we think that it is greater than that. We think the mu is greater than that. So it's a right-tailed test. Greater than is right-tailed because we're looking at everything to the right of 3.25. And it is mu because we're looking at the mean length of the phone call. Let's look at the last one. Using an old manufacturing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounces. With new equipment, the quality control manager believes the standard deviation has decreased. So here we're looking for standard deviation. We have a symbol for standard deviation. So our symbol for standard deviation is sigma. So our null hypothesis says that sigma equals, sigma equals 0.23. This was the old number, the number that we're given. The quality control manager believes the standard deviation has decreased. So we have H1 colon sigma is less than 0.23. So this is a left-tailed test because it is everything to the left of that sigma of 0.23. So hopefully that narrowed it all down for you. You have to look for the wording because in your homework it is going to mess you up because it'll give you the null hypothesis, it'll give you the P, the mu, and the sigma, and you have to choose which one it is. So be really careful when you're choosing that you're choosing the correct symbols and the correct null hypothesis based on the words. All right. So here are 4 different outcomes that you can get from your hypothesis test. You can reject the null hypothesis when the alternative hypothesis is true. This is correct. So if the alternative hypothesis is true, you reject the null hypothesis. You do not reject the null hypothesis when the null hypothesis is true. So basically, when you're doing your testing, if you cannot prove your alternative hypothesis, we fail to reject. We do not reject, or we fail to reject the null hypothesis because we didn't prove our our alternative hypothesis true. Since we didn't prove the alternative hypothesis, we fail to reject the null hypothesis. We didn't necessarily prove the null hypothesis, we just can't reject it. We reject the null hypothesis when the null hypothesis is true. This decision would be incorrect. This is a type 1 error. So if the null hypothesis is true, but we reject it, then it is a type 1 error. Do not reject the null hypothesis when the alternative hypothesis is true. This is called a type 2 error. So if we do our math and we showed that our alternative hypothesis was true, but then we didn't reject, that would be a type 2 error. So these are errors. This is going to come up in your homework. They're going to ask what type of error it is. There may even be a question on the test or the quiz. So this is really important. They're hard to remember, but just write it down in your notes. So basically, if the null hypothesis is true, but you say it isn't true, then it's type 1. If the null hypothesis is not true, but you don't reject it, then that's a type 2 error. So let's take a look at these. Let's do some examples and see if this will help you. So for each of the claims, let's explain what it would mean to be that type of error. So I want you to think about this. Think about what it would mean to make that type of error. In 2008, 62% of American adults regularly volunteered their time for charity work. A researcher believes that this percentage is different today. So we need to know, what would it look like to be a type 1 error and what would it look like to be a type 2 error? So think about this. I want you to think about it before moving on. So you might want to pause and think about it, or write down your notes, or at least just have it in your head. All right, so let's take a look at our answers. So a type 1 error. If the researcher concludes that the probability or the percent of adults that volunteer is not 0.62, if he concludes that it isn't, but it actually is, so if he says it's not, but it actually is, that's a type 1 error. Type 2 error. So if the sample evidence leads the researcher to believe that the current percentage is true, but then he doesn't, the percentages are, sorry, let me back up. So a type 2 error is made if the sample evidence, so if the researcher finds that the current percentage of people who participate in charity work is still 62%, his evidence is that it is still 62%, but the actual percentage differs. Let's go back. So we don't reject when the alternative hypothesis is true. That's our type 2. So we don't reject. So he's says it's still So he says it's still 0.62, but it isn't. So says it's true, fails to reject. To reject when H1 is true. So he fails to reject when your null hypothesis is different. So it is different from the 62%, but he's failing to reject. Let's take a look at another one. According to a study published in March 2006, the mean length of a phone call on a cellular telephone was 3.25 minutes. A researcher believes that the mean length of the call has increased. So let's take a look. So our type 1 error occurs. So if the sample evidence leads the researcher to conclude that mu is greater than 3.25, when in fact the actual mean call length is still 3.25. So the researcher is saying the mean is actually greater than 3.25 when it's really not. It is actually 3.25. Type 2 error. So the researcher failed to reject the hypothesis that the mean length was 3.25 minutes when it is actually longer than 3.25 minutes. So one of them is, so the first one is, he's concluding that that his hypothesis was true when it actually wasn't. And type 2 is, he is saying his hypothesis, his alternative hypothesis, was not true when in fact it is. Next. Oh, we didn't have the third one. Okay. So we're not even going to get into this. I'm not even going to go here. Let's just move on, because this is just going to confuse you. And actually, I believe there's a question about this. So I believe there's a question on this on the quiz. So alpha is the probability of a type 1 error. So alpha is your probability of rejecting the null hypothesis when the null hypothesis is true. Beta is the probability of a type 2 error. So it's the probability of not rejecting the null hypothesis when in fact the null hypothesis is true. So we have our alpha and our beta. So in your, believe it's a question in the quiz. So alpha is the probability of a type 1 error. Beta is the probability of a type 2 error. Just write those down. We're actually not going to use those anywhere else. And most likely, if you just attempt that problem, I'm just going to give it to you. So let's move on. So the probability of making a type 1 error alpha is chosen by the researcher before the sample data is collected. The level of significance alpha is the probability of making a type 1 error. So this is basically our confidence level. So remember when we were saying I'm 95% confident that such and such is true? So the level of significance is, and your critical values, your confidence level, are basically the same thing. So the type 2 error, it would be a beta, but we don't really use that. We use the type 1 error more than we use the type 2 error. So alpha would be our level of significance. As the probability of type 1 error increases, the probability of a type 2 error decreases, and vice versa. So these are, obviously they are opposites of each other. So if my type 1 error, the greater my type 1 error probability, the less my type 2 error is going to be. We never, this is really important, especially wording like in your final project, we never accept the null hypothesis because we don't have access to the entire population. We don't know for sure that the null hypothesis is true. We can say we do not reject, or I prefer to say, fail to reject. We fail to reject the null hypothesis, but we never accept it. It's just like the court system. We don't ever say somebody's innocent. We just say they're not guilty, because you can't prove innocence as much as you can just say they're not guilty. I guess you can prove innocence if, never mind, let's not even go there. All right. We are almost done here, guys. So this is back to the phone call. So the mean length of a call was 3.25. Researcher believes the mean length of the call has increased since then. So if the sample evidence indicates that the null hypothesis should be rejected, let's look at the wording of the conclusion. So this is much wordier than you are going to need to be. So the statement in the alternative hypothesis is that the mean call length is greater than 3.25 minutes. Since the null hypothesis, mu equals 3.25, is rejected, there is sufficient evidence to conclude that the mean length of a phone call on a cell phone is greater than 3.25 minutes. So that's like way wordier than you're going to need to be. You can just say there's sufficient evidence to conclude that the mean length of a phone call is greater than 3.25 minutes. You can just put that. You can just do that last little piece there. Let's look at the next one. Suppose the sample evidence indicates that the null hypothesis should not be rejected. Here's our wording of that conclusion. Since the null hypothesis, mu equals 3.25, is not rejected, There's insufficient evidence to conclude that the mean length of a phone call is greater than 3.25 minutes. In other words, the sample evidence is consistent with the mean call length equaling 3.25 minutes. You would just say, fail to reject. You can just say it's either not rejected, or you can say we failed to reject the null hypothesis. Hopefully all of this made sense. It's going to make even more sense once we're actually doing math with it, but at least this gives you the groundwork. I know the type 1 and the type 2 errors are a little bit confusing. Just remember that alpha goes with the type 1 error and beta goes with the type 2 error. You may need the level of significance because that level of significance is the probability of getting a type 1 error. As we said right back here, that the level of significance alpha is the probability of making a type 1 error. This is right here, this is important. That right there, the level of significance. You're going to see that when we're doing the math here pretty soon. So that right there is gold. Anyway, have a good day. If you have questions, send me a message, send me an email, and get ready to do some fun math in 10.2 and 10.3.